All right, welcome to computer number systems. So we have a few days of converting, adding and subtracting different base number systems. So I'd like have you take a couple minutes and read through this. And you should have the paper with you. And I'm probably going to ask you a couple questions about it. All right. So what we're going to be talking about is the decimal system, which is the system that we have now. It has 10 digits, base 10, okay? And the digits are 0 to 9. And you can count, you guys know the decimal system very well. It goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once you've gone around it once, it's 1, 0, 1, 1, 1, 2. And that's how all of these systems are. Binary is the most simplest, but it can get, obviously get you a little messed up sometimes. But 0, 1, those are the only two digits in a base system. And that's the system that computers think in. Okay, they think in on and off. In the old times, they actually used tubes, and one was on and one was off, and that told you something. So that's what binary is. And actually in binary, that's where the on-off symbol comes in. You know how you have on, well actually that's off, and on, so that's 0 and 1, on, off. Pretty exciting. I know you wanted to know that. Okay, then we have the octal system. It's not used as much anymore, but we do still have to know it in this course. And the hexadecimal. Sorry, there's something on my screen. And the hexadecimal, which is base 16. So base 8 goes from 0 to 7, and then loops back around. Basically, there are no 8 and 9. Hexadecimal goes all the way up to 9, and instead of having 10 as A, which would be very confusing because it's a 1 and a 0, they switched it to A, B, C, D, E, and F. So technically it goes up to 15, but we could have used any symbol. A, B, C, D, E, and F are just the ones they chose. They could have chosen pictures or something, but they chose letters, which makes sense. Oh, look, it says it right there. All right, so then let's count. So today and tomorrow, in class, when you do the work here, we're going to be counting in different number systems, just so you can get an idea, a feel for the different number systems. So the way I like to think of it as like a clock. Okay, and on this clock, every time you go around the clock, you get another, you add on another like tens digit in this case. So you add to the next digit. Okay, so we know we have the 1 spot. If you were to write out like 5, 2, 4, 7, this is the ones, the tens, the hundreds, and the thousands. So in binary, there's the zeros, and that's all we get. We get 0 and 1. So it's not even a clock, it's a line. So if we write a number in binary, like 1, 1, 0, 1, 1, this is the 1 spot, just like everything else is. That's always the 1 spot. But instead of this being, the next spot being the tens, this is actually the 2 spot. And then the next one is the 2 squared, or 4, and then 8, and then 16. So, that's how it's different. It's all base 2, and that's how it goes up. So, just to give you a basic example, you've seen decimal before, you know decimal. We count 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we've just went around this loop once. So we have gone around it once. So then we start back at the 0. And then we go around it again. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, whatever. 1, 9. And once we get to 1, 9, we've gone around it twice. And then we keep going to 0, to 1. And that's how it is in every number system. So this will keep going until we get to 99. Okay? There's 9, so we went around it 9 times, so now we're going to jump up to 10. And then it'll start all over again. And it'll basically repeat everything up to here with these 2 digits, and then go to 200. You guys know this innately, because you've been doing it since you started to count. But when we get to binary, it's kind of important that you remember that stuff. Binary is the one that messes with me the most when I do it. So I'm going to just switch over to octal, and hopefully, excuse me, that'll help us with like the decimal, and that'll help us with the binary. So I'm moving over to octal. Octal uses 0, 1, 2, 3, 4, 5, 6, and 7. Those are the digits. So when we get to 10, that's really 8. And this is why. 0, 1, 2, 3, 4, 5, 6, 7. So I just went around this circle here. 0, 1, 2, 3, 4, 5, 6, 7. Now I've gone around it once, so since I've gone around it once, I get a 1. And then I do the whole mess again. So 1, 0, 1, 1. Just like decimal, we just don't have, in octal, there's no 8 and there's no 9. So 0, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And then we get to 2, 0, because there is no 1, 8. And this one actually, the highest it goes is not 99. The highest this one goes is 77. Because this digit is the highest digit this one can get to is 7, and the highest digit that can get to is 7. So right after 77 would be 100. So we'll go 21, 22, 23, 24, 25, 26, 27, and then 30. Now we don't technically say 30, like I'm saying these things wrong, but you recognize these numbers, so we generally have to say 10, and oftentimes we write 10 with a little 8, so we know it's a base 8. But I'm in my little octal, excuse me, whatever, it just erased stuff, but I'm in my octal column here, so we know I'm octal. Like, I know that's what we're doing right now. So let's look at hexadecimal. This takes a while. I understand this is somewhat confusing, but it's a good practice, and it's helps the brain not get Alzheimer's or something. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no 10. There's an A. B, C, D, E, F. So there's 15 digits in hexadecimal. Okay, and so this one has more numbers, like more digits that we can use. So it not only goes up to, it not only has 8 and 9, but it has A, B, C, D, E, and F. So the first 15 digits are just these digits up there. So counting in it, 0, 1, 2, 3, 4. I feel like I'm wasting space here. Oh, but it's not 9 and 10. It's not 10 and 11. Should have stopped me. I'm kidding. Then after 9, it goes to A, B, C, D, E, F, and that's as high as it goes. Now, at that point right here, we have gone around once. So since we have gone around once, we now, in the next spot, in our 10 spot, which in this case is not 10s, 16s, we go 1, 0. So once we've gone around the loop once, we get to 1, 0, and then 1, 1, 1, 2, all the way up to 1F. And then after 1F, we're going to get to 2, 0, 2, 1, 2, 2. And I'm saying it right now. I shouldn't say 22. It's 2, 2, because we're in base octal. Okay, and I don't know how to actually, I don't even know if they have words like that. And then 2F. After we get to 2F, we'd be at 3, 0. So the highest this one would go, it would surpass 99. in decimal. 99 is lower. The highest this one's going to go is FF. Okay. So this would keep going to FF. And then it would get to 100 and repeat everything back here again. It's confusing, I get it, but we'll go through it, we'll kind of practice and count a little bit tomorrow, and hopefully you'll grasp this. Now binary gets really wide really fast. By wide I mean it takes up a whole lot of space this way, really fast. So that's why I kind of start everything on the side here, because you know it grows bigger. So this one, with binary, you go 0, 1, and then I've gone through this once already. So then I go to 1, 0, and then 1, 1. That's as high as it goes. So like octal can only go to 7. This one can only go to 1. So the moment I get to 1, I have to increase the next one. Well, this one can only go 1 also. So then after 11, that's 100 or 100. Okay? It's very interesting the way this works, and as we go through, maybe you'll notice a couple patterns. So 100 is next, and then all these 4 are repeated here. So it's going to be 1, 0, 1. Yeah, right here. So I just did the 0 spot here. That's here. Then 101, 110, 111. That's as high as that one goes. So now I'm at 1,000 or 100. Now all of these from here up repeats. So I'm just going to rewrite this whole thing, starting with this spot with a 1 in front. So 1001. Yeah, I just did that one. I wrote it first. That's the 0 one's right here. And then 1010. See that you just have to really concentrate when you're doing this. So that's the 4 or 3, and then it would just continue. I'm right here, and then I guess I can move down a little. So after 1100, I go to 11100. Then 1101, and then 1 whatever. Forget it. You get the idea. So to check yourself and how counting, you'll get it. We'll get there. Okay. Notice that in this column here, it goes 0, 1, 0, 1. This is the ones column. With binary, excuse me, this is still the ones column. This is the ones column here in octal, and the ones is always on the end. Always. There's always a ones. Okay? This one here is the twos. So notice that this one repeats every other one. 0, 1. There's 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Here, this is the twos. So basically, there's 2 zeros, 2 ones, 2 zeros, 2 ones. 2 zeros, 2 ones. And the next one, remember, is the 4s. So there's 4 zeros. I didn't write the zeros, but you can. Often people, when we write binary, we do include leading zeros. I don't know, we just do. Okay, so this column right here is the 4s. Just like I said over here, 1, 2, 3, 4 zeros, and then 1, 2, 3, 4 ones, then 1, 2, 3, 4 zeros, and it kind of keeps you on track. And the next one is the 8s, so there's 8 zeros and then 8 ones. It keeps the pattern going, and it's a very interesting thing. So just think about that, go through it, see if you can count the next few. I'll ask you probably a question about it, but we'll go over it more tomorrow. I know it's a little confusing. Have a great day. All right, today we're going to be adding. It's objective 2 in our binary octal hexadecimal mess. We're going to be adding, and I'm going to maybe include subtracting. I haven't decided yet. Oh, well, we're doing subtracting, but I don't know if it's today. So when you add, now this is decimal. Remember, this is base 10. This is our system that we're used to, we use every day. Okay? When you add 7 and 2 together, you get 9. Okay? Remember in decimal, 7, 8, 9. The moment we pass 9, we have extra digits and we carry. So remember, 8 plus 5 is 13. I'm bad with 8 and 5. Is 13. So we've gone higher than 9. So when we go higher than 9, we'd put a 3 here and we carry it here. Okay, and then 1, 2, 3. So that's decimal. You guys are aware of that. So let's try it with octal. So remember, with octal, the highest you can go is 7. So the moment you get to 7, if you go higher than 7, well, then you have to carry over. Okay, so 4 plus 2 is 6. Okay, there's a 6, so that's all right. 7 plus 3 is 10. So wait a second. What's 10? It's not 1, 0. Okay, it's, we go, oh, hey, what, I don't know why it does that. It goes here. We start here at 0. So we start at 7. Here's 7, and we have to go 3 bigger. 1, 2, 3. So that's actually, we went around once. So we're going to carry the 1 here. And then we went over 2 more. All right? So it's 7 around the circle, 8, 9, 10. All right, so that's 12. 1, 0, 1, 2, excuse me, not 10, or 1, 0 in decimal. So we're dealing with octal, so you have to just remember, it's like, we call it clock math, where you kind of go around in a circle, and every time you pass over, you get, we counted yesterday, you should know. So this is 5, 6, 7, 8. So if I get to 8 here, and oh, I remember how I could teach this a slightly different way. Anytime you have something here that it's bigger than our base, okay, so octal's base 8, so it's bigger than 7 here, you say to yourself, okay, I'm going to look at the number 10. So how many groups of 8? So how many, because I'm an octal, it's how many groups of 8 do I have in 10? Well, there's 1 group of 8, right? So that 1 goes here. That's how many groups of 8. Now we ask ourselves, how many left over? Well, if we take 8 out of 10, there's 2 left over, so that number goes there. Okay, so let's try it again with this one. This is 5, 6, 7, 8. So 8 is the number, it's bigger than 7, so we have extra stuff happening. So we say, how many groups of 8? Well, there's 1 group of 8. How many left over? 0. So this is 1, 0. So if I add 5, 7, 2, and 2, 3, 4, I get 1, 0, 2, 6 in octal. Alright, it's pretty cool. I like doing it. I'm going to do hexadecimal, then I'm going to go back to binary. Alrighty. So here we go. Hexadecimal is base 16. Remember, and when we look at it, it's 0, 1, 2, 3, 4, blah, 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 all the way up to F. And remember, F is 15. So when you add these together, we have to add in decimal because that's all we really know. And, well, that's all I can do. So E is, and I tend to have to write these out, so I'm going to write these over here. A is 10, B is 11, C is 12, D is 13, E is 14, and F, E is, oh, I hate when it does that. Sorry, E is 14, and F is 15. All right, so E is 14 plus 2, that's 16. Okay, so what you have to do, well, I think I did it wrong, whatever. So it's yeah, whatever. This is E here. E is, okay, 14 plus 2 is 16. So how, you look at 16 and you say how many groups of 16? Well, there's one group of 16. So that goes here. That's the carryover. Make that better looking. That's the carry. Okay? And how many left over? 0. So there goes a 0 goes right here. And then we just do it again. We have A and B and 1. We have to go add together for the next. This is 1, A and B. So I have to take A, well 1. A is 10. B is 11. So when I add these all together, I get 22. So ask yourself this question. How many groups of 16? Well, there's only one group of 16 in that. And how many left? How many left? 6, right? 16, 22 minus 6. So that's what we have. So remember, the leftover goes here. And, I mean, how many groups goes here and how many leftover go here. And then 5, 6, 7, 8, 9, 10. So 10 is A, so then we write 10. I find this actually a lot of fun. But you just have to get used to the different bases, and you ask yourself how many groups. Remember, the groups go in the next line, in the next kind of column. And leftover goes here, right underneath the original. Okay, and then we do binary here. So this is binary is base 2, so we're doing a lot of groups of 2. How many groups of 2, and that's so forth. So for the first one, 1 plus 0 is simply 1. And then on this one, 1 plus 1 is 2. Well, we can't have a 2 in binary, so you have to say how many groups of 2? Well, there's one group of 2, so that carries over here. And how many left? There's 0 left, so the 0 goes here. So now the next one, we add this, this, and this, and we get 3. And this is basically the only 2. As long as you're only adding 2 things together, you got to do 2 and 3 over and over. So you get a 3. So how many groups of 2? There's one group of 2, and how many left? 1. Okay, if you subtract 2 from 3, you get 1. So this one goes here, and the other one goes here. And then 1 plus 0 is 1. 1 plus 1 for the next one is 2, so that's the same as the one we just did here. So the groups goes here, and the leftover go here. And 1 plus 1 is 2 again, so again, 1, 0. 1 plus 2 is 1, 0. So that's all it is. So there we get when we add it together. All right, we'll practice this tomorrow and see how it goes. All right, subtraction. When we subtract, so remember when we subtract in decimal, if we subtract something bigger on the bottom than on the top, we have to borrow. And we always borrow, in decimal we borrow 10 because we're base 10. So here in this case, I can't borrow from a 0, so I have to come back over here and borrow from the 5. So I put a 4, make this 10, and then I borrow this, make a 9, and there we go. Okay, so you guys all know how to subtract, but if you take 1 away from 50 here, you get 49. So you have to take this 0 down 1, from 10 to 9, and the 5 down to a 4. And then you do 13 minus 4, which is 9, 9 minus 6, which is 3, and 4 minus 4 is 0. So you're left with 39. Okay, so borrowing and that kind of thing, you have to do in octal and in hexadecimal. So with this one, again, we still can't subtract 4 from 3, so we have to borrow. Now when we borrow with octal, this goes down to 6 still, but we borrow 8. We can't borrow 10. We can't put 1, 3. Okay? Because when we subtract, we still subtract in our world. So we borrow 8. So this is no longer 3, this is now 11. Because 8 plus 3 is 11. Okay? So then we do 11 minus 4. 11, which is 7. Okay? And you should never get anything bigger than 7 when you do it this way. And then 6 minus 0 is 6. 2 minus 1 is 1. 167. Okay, hexadecimal. Same thing here. D, I have to do this every time. A is 10, B is 11, C 12, D 13. I didn't mess up that time. Okay, so 7 minus D. So we're trying to do 7 minus 13. We can't do that. So we have to borrow 1. But when we borrow from hexadecimal, we're borrowing 16. So we take 1 away from A. When we take 1 away from A, we go to 9. It goes from 10 to 9. Right? When we borrow 1 from and we give it to 7, we're actually borrowing 16. So 7 is no longer 7. It is 23. Okay, because 16 plus 7 is 23. Am I messing with you yet? So this is 23. So then we do, instead of 7 minus 13, it's 23 minus 13, which is 10. And 10 is A. This is like so much fun. Okay, so then we do 9 minus F. So 9 minus F, F is 15. Well, I can't do 15, subtracted from 9, so I borrow 1 from here. And when I borrow 1 from there, I'm borrowing 16. So this isn't 9 anymore. It's 16 plus 9. So 16 plus 9 is, can I just erase that? Oh, good. 16 plus 9 is 25. So when I subtract here, I get 10, which is again A. And then 4 minus 3 is just 1. So if I subtract 5A7 from 3, and I subtract 3FD from 5A7, I get 1AA in hexadecimal. And finally, binary. I don't know why I do this one last, I just do. Okay, 0 from 1, we can do that. 1 from 1 is 0. If I'm taking 1 here, subtracting it from 0, I can't do it. When I borrow, I subtract, I take 1 off. When I take 1 off, I'm borrowing 2. This is a binary system, so I'm borrowing 2. So 2 plus 0. So 2 minus 1 is 1. And then this is already 0 because I borrowed 1, so I'm left with 101. Okay, again, we'll practice this tomorrow. It takes a little while to get used to. We'll see how it goes. Okay, extra page. Oh, okay. So with this next thing that we're doing, we are doing converting. Converting takes a little bit of effort. But what I just have an extra page here so I can remind you of a few things that we tend to do when we're young and we're learning about decimals. So if I say I have 5,902, and this is base 10 or decimal. Okay, we put a 10 here if we're not sure, because we do a lot of different number systems, what number system we're using. So right now we're using decimal, our normal one. We always do. Now I can expand this to be 5 times 1,000 plus 9 times 100, because this is the thousands, hundreds, tens, and 1 spot, right? One spot. 0 times 10 plus 2 times 1. Okay? What you'll notice is what place you're in is how many zeros you have. So I'm in the first spot, I have no zeros. I'm in the second spot, 10, I have 1 0. And it's pretty I don't know. I like it. So I can rewrite this using an exponential form, and it makes it a little bit clearer what I was just trying to say here. Plus 2 times 10 to the 0. Remember, anything to the 0 power is 1. So that's where this 1 comes from. So if I'm in the, excuse me, I'm here, I'm raised to the 0 power. Here's first power, second, third. It's the position that you're in. And in computer programming, our positions always start with 0. Okay, so if I'm in this first position, I'm at the 0 spot. Second position is 1, 2, and 3, and 4, and 5 as we move on. So this is how it works, but instead of base 10, we're going to be having like base 2, and base 8, and base 16. So this is how this is going to be used when we do some converting. So let's do some converting now. All right, so the first thing we're going to do is we're going to convert from binary to decimal. Now notice I have a base 2, and that's again just to have you realize that, because that's a real number in decimal. You know, what is it, like 1,100,101? It's not that in binary, but that's how it is. So just to keep you straight and just to get you in the right frame of mind, when you're converting to decimal, so that's what we're doing. You see a 2 decimal, you multiply. So we're going to be multiplying. We multiply. All right, and what we multiply is those positions that we're in. Okay, so when you're in binary, any system at all, this is position 0, 1, 2, 3, 4, 5, 6, and that is the exponent on the base. So the base in this case is 2. So if I want to convert this to decimal, I have to multiply by that. Okay, so this is 1. 1 times 2, but that's the base, to the 6th power. Because I'm in binary, I'm in base 2. If I was in decimal, I would be a base 10, octal base 8, hexadecimal base 16. It's the exact same thing with every single one of them. If I want to convert to decimal, this is it. So, and then I do a plus, just like we did, you know, what I was explaining with 5,902. All right, then it's 1, oh no, I switched everything around. Then it's 1 times 2 to the 5th, because this is the 5th position here, plus, and then on here, 0. Whatever this digit is goes here, and then times 2 to the exponent is the position that you're in. So 4 plus 0 times 2 to the 3rd, plus 1 times 2 squared, plus 0 times 2 to the 1st, and plus 1 times 2 to the 0. Okay, now when you start doing this and you're converting all the time, you can literally just skip the zeros because it's just 0. You know, this is going to be 0, this is going to be 0, and this is going to be 0. I just wrote it all out so you could kind of get a gist of what we're doing, but you can skip the ones with the zeros. And then we just simply do the math. 2 to the 6 is 64. And we multiply it by 1, but in binary it's just 1, so it doesn't really matter. Plus 32, which is 2 to the 5th, plus over here, 2 squared is 4, and then over here 2 to the 0 is 1. So you'll notice anytime you have a 1 over here, and maybe you understand it more now, you'll always have an odd number. So this is going to be 101. If that 1 wasn't there, it would have been even. So exciting, right? All right, let's, so octal to decimal, do the exact same thing, but it's base 8. So the positions are 0, 1, 2, and we're just raising it to the 8 power. So you take the first digit, 5, times 8 squared, plus 2 times 8 to the 1st, plus 3 times 8 to the 0. And then you just figure out what this number is. Now, it's not as easy as binary. So, but you just, you know, you have calculators. So this is 320. This is 16. This is 3, because 8 to the 0 is 1. Add them together, and you get 339. So if you were looking at 523, that's actually 339 in decimal. Okay? And moving on. Hexadecimal. So again, here we go. We have position 0, 1, and 2. So this is base 16, so that's the base we're using. So it's 2 times 16 squared plus 4 times 16 to the first plus d, and d is 13, times 16 to the 0. And you just figure out what this number is. 512, 64, and 13. Add them up. It's 589. So to go from 24D in hexadecimal is the same as 589 in decimal. So to go the other way, to go from decimal to binary or decimal to anything, you do the opposite. Instead of multiplying, we divide. Now there are hundreds of different ways to do this. I found this way to be the easiest. If you know another way, go crazy. I don't care. Okay, I can math and I can figure it out. But this is how you do it. You divide by the base that you're converting to. So I want to know what 234 is in binary. So that's base 2. So I take this thing and divide it by 2. And what I have to keep track of is it's like modulus division. If you know what that is, I have to keep track of the remainder and the quotient. So you have to long divide. Calculators really don't work. With binary, it's pretty easy because if you have a 0.5, then the remainder is 1. But in general, you are going to want to do the long division the long way. So I'm going to just kind of show you what I mean by that. So I have a 2. I put these numbers above it just to keep me in track. Those aren't part of the problem, but I remember that I'm dividing by 2 here, and the original number was 234. It's just one of those. Okay, so I divide. So I take 2 into 234. I'm going to show it the first time, and then I'm not going to show it other times because with binary it's really unnecessary. Okay, if you don't remember how to do long division, we'll talk about it tomorrow. Okay, so here it is. This is the quotient, that's the Q column, and this is the remainder, that's the R column. So my quotient is 117 and my remainder is 0. And then I do it again. I take 2 and I divide it into 117. I get 58 for the quotient, and I get 1 for a remainder. And I continue on. If I divide 58, I get 29 with no remainder. With 29, I do 14 with a remainder of 1. I divide 2 into 14, I get 7 with a remainder of 0. And that's just me doing this math here. I'm just doing it quick, because I can. And then if I divide 2 into 7, it goes in 3 times with 1 left over. And then I divide into 3, it goes in once with 1 left over. The moment this is less than the base, in this case 2 is the base, we're done. Okay, and you can stop. You just start with this number, write this number out, and go up. So that means this 1 is here, so that's the first number in binary. And then 1, and then 1, 0, 1, 0, 1, 0. That is 234. In decimal, it's 11101010. Okay, in binary. That's all. So you just have to practice this to get used to it. Let's go from decimal to octal. So it's the same thing. In just this case, it's a little bit more difficult because you have to divide by 8. Okay, so I like to set it up again like this. This is your remainder. This is your quotient. I'm dividing by 8. and 339 was my original. Okay. There are tricks to using your calculator. We'll go through it. It's a lot easier to show you in person, but this is generally pretty quick. So if I take 8 and divide it into 339, it goes in 42 times with a remainder of 3. If I divide 8 into 42, it goes 5 times with a remainder of 2, because you know 5 times 8 is 40. There you go. Okay, this number is less than 8, so I'm done. So I start with this one and I go up. So the number 339 in decimal is 5, 2, 3, and octal. Okay? And then we do the exact same thing with hexadecimal. Okay? We divide, because we're to something else. We're from decimal to something else. We divide by the base. So the base is 16. So I take, I'm going to go to blue, remainder, quotient. So 589 is the original, and I'm dividing by 16. So if I divide 16 into 589, it goes 36 times with a remainder of 13. The remainder is different than the decimal thing that you get when you divide. So you need to figure out how to get that 13 out of there. I'm fairly confident you can do that. 36 isn't less than 16, so I divide 16 into 36. It goes twice. That's 2 times 16 is 32, so there's 4 left over. This 2 is less than 16, so I'm done. Once the decimal's value, hexadecimal, you know, it gets bigger, we can do less. We do less dividing. Binary, there's only 2 digits. So 2, 4, 13. So 2, 4, and 13 is D. Done. Okay, finally, converting from binary directly to hexadecimal or octal, or vice versa, or it's fantastic. Okay, so we're sticking with binary, and we want to go to an octal or a hexadecimal. And no, we don't want to go to binary in between. What we want to do is we want to take each one of these little sections here. There's 4 sections, well, there's 3 sections of 4 here. Each one of these is a digit of hexadecimal. So what that means is, let me just kind of break this out over here a little bit so you can see. If I look at 1010, that's just this first one right here. This is position 0. This is 1, 2, and 3. And remember when we wrote this out and we were converting to decimal? This one was 2 to the 0, or 1. This one was 2 to the 2 to the first, or 2. This one was 2 to the third, or 8, or 2 squared, or 4, and this one was 2 to the third, or 8. Now what happens when you add all these together? You get 15. You get 15, which is exactly the number of digits. You know, we don't include the 0 because it's just 0. 0 to 15, or E, for hexadecimal. So when we're converting from binary to hexadecimal, each 4 digits, each group of 4, is 1 digit of hexadecimal. So this is how you do it. It's so easy. So 1101, that's one group. 0011 and 1010. So I'm going to label it with these numbers. 1, 2, 4, 8. 1, 2, 4, 8. Each one of these groups could be any number from 0 to 15, which is what you can have in hexadecimal. So if I come over here, we have 8, 4, I don't need this one because that's 0 and 1, so I'm going to add 8, 4, and 1, and 8, 4, and 1 is 13. This one I only need to add these 2, which is 3, and this one I add this one and this one, which is 10. So 13 is D, 3 is 3, and 10 is A. So converting right to it, it's D3A. Bam! Done. It's awesome. So when we want to do to octal, so the next one is octal, we want base 8. So we want 0 to 7. So that is, we just need, let's do it this way, we only need these three. So it's 4, and 2, and 1 is 7. So we want to be able to go from 0 to 7, and that's what we can do with 3 digits. So when we want to go from binary to octal, all we need is groups of 3. So we need these 3, then these 3. So so this one is going to be a 1, 2, 3, 4-digit octal number. So with octal, you need 3 digits. So 0, 1, 0. And then next group here, 1, 0, 1. And then 0, 1, 1. And then I put 1, 2, and 4 underneath them. Remember, we're not adding these together. Each one of these is a digit of octal. That's what makes this so easy. So here we need all the digits, 4, because anywhere there's a 1, we add the 4, the 2, and the 1, because remember, we would multiply by it. So 4 plus 2 plus 1 is 7. The next one, all we need is the 2. This one is 4 and then 5. And this one is 2 and then 3. So from whatever that is to octal is 7253. That's so awesome, right? Tell me it's not the coolest thing. Okay, then to go from octal to binary, pretty much the exact same thing. I'm going to set it up. When you're done looking at your work, it's going to look the same, but we're kind of going the opposite way. So what we want is each one of these digits, 6, 4, 7, 2. In binary, remember, it's octal, so we need a group of 3. Okay, so I want this number, and I'm going to label it with the numbers below that we had before, just to make life a little easier. Okay, if I want to get 6 out of 4, 2, and 1, I need a 4, I need a 2, that's 6, I don't need the 1. So if I want to get a 4, there's the 4, I don't need 2 or 1. If I want a 7, I need all 3. And if I want just a 2, I have a 2 right there, and I don't need those. I know it, it's just adding. Add these, what do you add together to get 6? 4 and 2. But you have to use a 4, 2, and a 1. And that's it. So the binary equivalent of that is 110, 100, 111, 010. And then lastly, to do to hexadecimal, instead of groups of 3, it's groups of 4. So E, I'm going to write it on top so it just doesn't get in the way. It's 1, 2, 4, and 8. Remember, that makes 15. 3, 1, 2, 4. 1, 2, 4, and 8. B, we need 1, 2. 1, 2, 4, and 8, and 4. Alright, so, to remind yourself, E is 14, you may have to write it out, and B is 11, just as a reminder. So if we want to get E, or 14, you have to just figure out what you should add together. If you add them all together, you get 15, so you don't need the 1. 8, 4, and 2 is 14. We want 3, just need those two. Anything you don't add up gets to be a 0. This one, 8, 2, and 8, 2, and 1 gives you an 11. And if we just want a 4. And if it was 0, they would all be zeros. That's it. And so that's the binary equivalent of E3B4 in hexadecimal. Alrighty. Cool. Bye.